So as promised, I'm going to discuss what really the significance of the difference quotient is. And I'm going to do so by talking about secant and tangent lines. So consider the following function here. So let's just call this function f of x. So suppose we had some function f of x. And let's just choose two arbitrary points on f of x. Let's go ahead and just label this point right here and call this one point P. And we'll just find another point and we'll call this one point Q, for example, okay? And suppose I wanted to find the slope of the secant line. So let's talk about that. First off, what is a secant line? The secant line is a line formed by intersecting any function at two different points. So suppose I just went ahead and I drew this line. That's not very good. Let's see if I can clean that up a little bit. There we go. Okay, so suppose I had some line like this. This is our secant line, okay? This is our secant line. And it's intersecting our function at two different points. And suppose I wanted to find the slope of the secant line. So if I want to find the slope, we remember, we're going to need our x and y values of our two coordinates. So we're going to call this one right here, this particular point P. Let's say this is our x1, and this will be our y1. So this point right here, we'll say this is our y1. And this, for this point right here, we'll call this our x2 and our y2. Okay? And so if I want to find the slope of this secant line, so I'm going to say m, and this is for our secant line here. Remember, we can just use our slope formula and say this is y2 minus y1 over x2 minus x1. That's just basic algebra. Now, instead of defining these points just in terms of their x and y values, I want to think about them a little bit differently. I want to think about these coordinates in the context of the function. So here's what I mean by that. So first off, instead of calling our first x value just x1, let's just call it x for now. And what that means then is this y value is no longer just y, but it is the output or the result of our function when we plug in x. In other words, when I plug or evaluate our function at x, I get some output, which we'll call f of x now. So what I'm going to do is I'm going to rename our y1 as f of x and call our x just x, or excuse me, x1 are just x. And now I'm going to do the same thing for our x2 and y2. So instead of calling this value here x2, I'm going to say that this x2 value is some value that is h units added to whatever x is. In other words, we can call h this value here. So if that is the case, then this new x value would be whatever x plus h is, right? So we're just adding some horizontal distance to x, and that gives us our new x plus h value. So if that's the case, this y2 value up here now, is actually called f of x plus h. It is the result of what happens to our function when I evaluate it at x plus h. It gives me some output. So if that is the case, let's think about what that means for the context of our slope here. It means our secant line, instead of just calling it y2, I'm going to call this f of x plus h minus y1, which is now just f of x. Our x2 became x plus h minus our x1, which was now we're just calling x. So this can be cleaned up even further by calling this f of x plus h minus f of x all over, well, x and negative x are going to negate one another, and we're just going to have h. And does that look familiar to you? There it is. There's our difference quotient. So all along, our difference quotient has simply been a fancy way of describing the slope of our function. That's all it is. It's And that's in fact one of the names for it. We call it the fancy slope. It is a way of defining the slope of a secant line. Instead of using x1 and x2 and y1 and y2, we describe those points in terms of their placement in the function. I mean, and that's pretty big. I'm just going to leave this guy over here because I think that was huge. So our difference quotient is really just the slope of our secant line of our function. Well, what application does this have to calculus? Well, in our previous lesson in 11.2, part 2, we found the limit of our difference quotient as h approaches 0. So let's think about that now in the context of what we just drew. As h approaches 0, ask yourself, I'm going to highlight this here, if this h value gets smaller and smaller and smaller, right, so that q is getting closer and closer to p, think for a second about what that means for our secant line. It would mean the following. If h gets closer and closer to 0, that means this secant line will actually get closer and closer to being that of a tangent line. And just to highlight that, let's just go ahead and demonstrate it this way, right? So what happens as q gets closer and closer to p? In other words, as h, which is the horizontal distance between p and q, as that gets closer and closer to 0, q is getting closer and closer to p. And that secant line is getting closer and closer to being that of a tangent line. It's not exactly on, but you get the idea, right? It's right on top of being a tangent line. So again, and now I can't get, there it is. Q, as the h value gets closer and closer to being 0, that secant line gets closer and closer to being that of a tangent line. And again, what's a tangent line? A tangent line is a line formed by intersecting f of x at just one point. The slope of the tangent line equals the slope of f of x at the point of tangency. In other words, the slope of our tangent line is the limit, and let me just write that out here, the limit of our difference quotient as h approaches 0. And in calculus, we have a special name for this. This is called the derivative. You know what? And I'm going to put that again. Just because I think it's that cool. All right, that is our derivative. The derivative is the limit of our difference quotient as h approaches 0. And the derivative, what it effectively is, other than what I just described, it's a function that gives us the slope of our function at any given point. So I can choose any point on my function, and I can find the slope of that function at any x value. That is what we call the derivative. And it has a couple of different notations here. F prime of x, dy dx, y prime, the derivative of f of x with respect to x. These are all different notations. You'll see them through various textbooks, but the big thing is that you just simply understand what's going on there. So let's practice finding the derivative using this limit process. There are going to be a couple of ways that you're going to learn to find derivatives in calculus, but for now, we're just concerned with using the limit process of our difference quotient. So let's try a problem here. So we're going to find the derivative using this limit process of this function, 5 minus x squared. And I went ahead and I just graphed it for you. And specifically, we're going to choose the point 2, 1, which is this point right over here. Here's 2, 1. And we're going to try to find first the derivative, and then we're going to find the slope of the tangent line at that given point. Okay? So we're going to say the following. Let's just go with this notation here. We call this f prime of x. Our derivative is the limit of our difference quotient as h approaches 0, which is going to look like this. Okay? Now, let's evaluate our difference quotient. Let's find our difference quotient for this specific function. So we're going to say is equal to the limit as h approaches 0 of 5 minus, and we're going to replace our x with x plus h, minus 5 minus x squared. And if you need practice doing this, just go back to my previous video and we did some practice with these. So we're going to say the limit as h approaches 0 of, and we're going to expand all this out, 5 minus x squared minus 2xh minus h squared minus 5 plus x squared, and all of this over h. And as you can probably tell, we're going to have a chance to do some cleanup here. So let's just go, let me actually use my highlighter here so that things don't get too messy. So I got a 5, negative 5, positive x squared, negative x squared. And I can also divide out my h down here with these. And what we're left with is just negative 2x minus h. Here we go. Now let's find the limit of this expression as h approaches 0. Well, as h approaches 0, this is just leaving us with negative 2x. Okay? So there's our derivative. We're going to say f prime of x is equal to negative 2x. And we found that derivative using, the limit process of our difference quotient here. Okay? So now that we have that, let's go ahead and let's find the slope of our tangent line. Let me use a different color for this. Let's find the slope of our tangent line at 2, 1. So at 2, 1, let me just go ahead and just draw a tangent line here for you. And that's not very good, but I'm just going to go ahead and kind of cheat there. There's my tangent line, looking good. So what is the slope of this tangent line at 2, 1? Well, we know that our derivative is negative 2x. Well, what's our x value here? Well, it's 2. So it's simply equal to, so, I'm going to go ahead and write this. F prime of 2 is negative 2 times 2, and that's equal to negative 4. Okay? And see if that matches up with what we have here. So at the point 2, 1, ask yourself, does this slope of that tangent line, would it be positive or negative? And does it look to be as steep as negative 4 here? And it does, right? And you can kind of just test other points here and just kind of see intuitively if it makes sense. For example, what would the slope of our tangent line be at 0, 5? Well, our tangent line would look something like this, right? Our tangent line at 0, 5 would be something horizontal. Well, would that seem to match up? What is f prime of 0? This is at the point 0, 5. Well, it would just be negative 2 times 0, which is just 0. And that makes sense. It has a horizontal tangent line. Okay. So hopefully this video kind of finally gave you the value and intuition for what was going on with our difference quotient. Turned out the difference quotient is just a fancy slope. It's a way of finding the slope of a secant line that intersects a function at 2 points. Finding the limit of our difference quotient gives us the slope of our tangent line. And in calculus, we call that our derivative, which is simply a function that gives us the slope of f of x at any value of x. So with our derivative, I could choose any arbitrary point on our function and find the slope of our tangent line there. There are some problems here on the back that I am going to just leave you to do, but I will post the solutions in our classroom and in our school loop.